Good afternoon. So everybody can hear me. Let me see if I get a response.
Yeah, I can hear you.
Okay, thank you for telling me. Yes, excellent. Thank you, thank you. So let's wait a little bit for more students sign in. Thank you, Josh. So let's, yeah, I think I need to wait because I only have 2/3 of the students in here. Let's wait a little bit. So the basic, this is week number 3, lecture A. We are still in this continuous 3 weeks of mechatronics components part of the course. So the components, as you can see, I put more emphasis on mechanical components, electrical components. But giving all those components, can we construct the model? Okay, we need the model. Okay, we need the model. And in the end of this lecture, I'm going to getting started for a most important component is called op-amp. Okay, so I'm going to tell you why op-amp is important. Yeah, it is so important that you should really invest in that. We had a very good office hour as well, and a lot of questions, and we went through of the questions. So the purpose of the homework is to force you to go back and read the text, even you need to Google for the answer, or learn the background, like what is transistor, what is transistor logic, and so on and so forth. Okay. So here's today's plan. We have 3 parts. Okay. The first is to quickly review what we learned last week regarding modeling and components. Okay. The second is I'm going to run 2 examples, computing with numbers as well as symbols, to see how we can build the state space model. Then after that, I'm going to start a little bit with motivations of amplifiers. Okay, amplifiers. And today's quiz is really, really simple. Okay, and so please get the quiz and just put in the answer. Is a multiple choice. Okay. So with that, I'm going to share my screen. So we're going to walk through today's lecture. So this is basic components. Okay. I think I'm sharing the screen here. Oh, I already shared. I already uploaded the files. Okay, so we are here. Okay, we talked about model types. We talk about electronics in the modeling is important either way. So we talk about how to unify 2 types of variables. One is through variable, one is a cross variable. Like through variables like current, force, okay, heat transfer rate, fluid flow rate, mechanical components, MSD, mass spring damper, and talk about electrical elements, IRC. Okay, actually we should say like we should not see it's a CLR, okay, CLR, MSD. Okay, but I also introduced last time briefly to you about Memristor. So I'm hoping that you will be able to appreciate this new knowledge. It's It's not in the textbook yet, but we should have a fourth elements, electrical elements. This is called missing element, Memristor. So we have this kind of analogy, and then we'll be able to, based on the components, remember you played with Lego, Mindstorm, Lego technique. You can build the system from building blocks. So then we can start to use all these unified components to build systems. And so we went through the steps to build the system, and we use a method. Actually, in our textbook, there's a dedicated section talking about linear graph method. So the linear graph method is nothing but a more generalized view of KVL and KCL. Okay. So state space, we keep talking about state space, but you should know the state variables should be unique, independent. Okay, like C1, C2 here should not be a state variable. You can use only one of them. Okay, or combine equivalent capacitor. So then we end up last lecture, Friday, with a state space model example for this diesel engine driving a pump. So then what we should do is to decompose this system into different parts. And each part will using Newton's law, Newton's second law to get this equation. Then there's a coupling between them, okay? This is actually a connection, like you have branches, you have nodes, okay? Then you apply the principles of KVL, KCL, then you will be able to get all the equation of motion out, okay? I think I should remove this one, hide floating meeting control. Yes, this is better. Okay. On the other hand, we continue to say that state space model is just a model. There are infinitely many, okay, models to describe the same thing, okay? So for example, your X can be actually scaled up and down with different coefficients in here. There are infinite possibilities. So giving this type of translatory system, we have in homework question, okay? We have this type of mechanical system. This mechanical system has mechanical elements and put together, okay? So you are mechanical engineering students. You are learning, I heard you are learning component design this semester. You are learning vibration in parallel with this. This is good. This is very good. So today we are going to run something similar with two examples. The first one is simple one. It's a relatively simple one. And the second one is a little bit harder, okay? So let me do this week 3 here. So I have an example. Actually, we should go this one first. No. Wait. Give me a second. Why I don't get this? Okay. I think I need to make it editable so I can add comments. Then when I add comments, I need to remove this one. And okay, I think this is great. So sometimes this modeling approach, we are using a linear graph theory, okay? So this is from Clarence de Silva's Mechatronics book, he said that way, okay? Which is okay. I kind of like that framework. I'm okay with that. So, but in other textbooks, they don't call it linear graph theory, okay? They call state variable technique, okay? We have MATLAB standard tools to do all this. So I'm going to use the following IRC circuit to show you how we can build state variable technique, okay? So this is an example we are seeing here. Can you see this one clearly, especially those small signs of a, can you see it clearly? You have a source, okay? And you have a resistor, you have capacitor, you have an inductor. Sorry, this is the inductor. So this is another inductor, okay? No, this is supposed to be a load, actually, sorry. This is 1 ohm is the load. So this is a load. So this is R, this is C, this is L, this is R. So this is also R, but this RL is a load, okay? So in this case, what we're trying to do is trying to see what is the governing equation of that. And we have energy storage element in here. So we are trying to build a governing differential equation of this. Why we need a differential equation? It is because we are no longer at high school level. For high school level, we care more on the steady state, okay? Steady state, static relationship, RC networks, or just a resistor network. But here, we're assuming that V of S is a general time varying signal, and how other variables will be changing over time, okay? So it's all dynamic and transient, okay? Dynamic and transient. So if we drop, you can see we didn't drop the bracket T here. So we understand implicitly everything we are talking about is time varying. It will change. Change is also called evolve. Then when you evolve, you change according to what? You must follow certain ways. So that according to what is called governing equation is our ODE, ordinary differential equation. There are two types. One is called scalar. You have only one variable. You have a multi-variables, okay? So it's a vector type. So let's continue. So you have a capacitor in here. So this equation is called constitutive equation. So how those across variable and through variable are connected. So fortunately, the C is 1. So fortunately, this is dVc dt. So I think everybody knows. So these two are energy storage element. So this constitutive equation, wait. So this is another constitutive equation. So you have these two. So step, okay, let's do this. So this is a step 2, writing the constitutive equation. What is the step 1? Step 1 is to identify, for capacitor, you assign a voltage to it. For inductor, you assign current to it. Use these two as state variables. Why? Why I forgot this? There is actually a rule of thumb in here. They said it. Okay, please focus here. So how you choose state, so step 1, how you choose state variable. So for A-type energy storage element like C, okay? Then A cross variable should be the state variable. That's voltage VC, okay? For the, so this is IL, this is VC, okay? IL, VC. So they already told you the rule. And for your mechanic systems, they follow the same rule. Did you get it? Okay. Then step 2, we write constitutive equations. Okay, constitutive equations like a capacitor and an inductor, they have a relationship. Okay. So then the step 3 talk about continuity equation versus a compatibility equation, like conservation. Okay. Then you eliminate the redundant variable you express in terms of state variable. So this is what we are doing here. Step 3, we just check current voltage for rest of the current state variable. So in this way, we are using a KVL, KCL. Then we can write it down. And for the KVL to the left loop, okay, this one, KVL means VS equals this voltage and plus this voltage. So it's VC, and this is what? This is 0.5 and times the current. Well, the current has 2. So because this one, and this one, adding here should be, so one is the voltage here is a dVc dt. This is this current. And this one is from IL. Okay, this one add together will be this one. But remember, we are using a different notation here. Be careful. Okay, so we are using a different notation here. So if according to what we have in here, so you should have, if you have something goes in, that is positive, so this one should be also goes in, okay? Goes in, this goes in to this node, okay? At this node, I know from KCL, the current in here should be this plus this. So that's why we have this one, okay? So that's a KVL on the left loop, this loop, and a KVL on the right loop, okay? So you have a IL, VL. So this is V voltage in here. This IL is the times 1, okay? Is the voltage here. So then minus is VC, okay? This should be 0. This should be 0. So I have a simultaneous equation here and here for the KVL, KCL, and I also have this connection. So what we are going to do next is to write 2 simultaneous equations. From the left-hand side, this is your state variable, VC is your state variable, IL is your state variable. You do derivative of it. You represent it in terms of other variables. So you have this one, and then you have this one, okay? So you have 2 simultaneous equations here, okay? So you can see all these are state variable, state variable, state variable, state variable. But this is the input term. VS is the source. It's here. It's the source. So after that, we can write equation in the compact matrix form. Okay, compact matrix form. So then you can see this is VC dot equals -2 VC minus 1 IL. So it's kind of lesser. No, don't do that. So you do this cross product. Then it's a 2 VC minus 2 IL is this one here. And plus 0 times this. So this is 0. But this one is plus 2 VS. So you have 2 in here. So writing this as X. So X dot equals AX plus BU. So this is called matrix form of state equation. So this is actually a first order ODE in vector form. Okay. But what if I do something like this? Can you guys see my whiteboard?
Yeah.
Okay, I'm going to derive something on the whiteboard for you. Okay, great, thank you. So what I do is here is like a VC dot is 2VC minus IL plus 2VS, okay? Then I have a IL dot is 2VC minus 2IL. Do you see that? So then you can see what I'm trying to show you is I can eliminate the IL. I eliminated IL by doing what? So I can always write this one in terms of second order ODE, okay? Second order ODE, okay? Second order ODE. Because I said here is first order ODE, vector form. I can do a second order ODE in scalar form. Can we? My answer is yes, we can. Let's do it. So let's do it. If we do here, we can see that we can eliminate. So let's say, for example, you have a VC double dot is 2 VC dot, okay, minus IL dot plus 2 VS dot, right? So then you can say that you can say that this is the VC dot. So you can put this IL into here. So this term you can get from here, right? And also you can do this term in here. You can get it here. So my purpose is to eliminate IL. Okay. So clearly this is possible. It's just a little bit tedious. Okay. It's a little bit tedious. So it is possible to do. But you may say this is kind of difficult. This is kind of difficult to do. There is a way to do that. It's called Laplace transform. Laplace transform. Okay. So what you do is SVC is you do Laplace transform here. The minus 2VC minus IL plus 2VS. Okay, so you have SIL is 2VC plus minus 2IL. Okay, so then you can try to eliminate the IL. Okay, try to do elimination. Then you get everything is so let me do this. Let me show this one to you. So you have a IL, you can do this way. So from here, we are going to get IL, put everything is SVC plus 2VC plus 2VS. So you put all the terms, okay, it's minus IL. For this term to this side, So you end up with this alone. So you have this one and you have this one, okay? Then you put this one in, okay, put this one in. Actually, we don't do this. Actually, let's just directly solve this. I have RL, so this is S plus 2, and it's 2VC. So then I have IL is 2 over S plus 2 VC, right? So then I started put this RL inside here. I'm going to have SVC in here. This term is minus 2VC minus 2S plus 2VC minus 2VS. So then it's solved. We don't have the IL anymore. So then we just multiply S plus 2. So S plus 2 VC equals 2 S plus 2 VC. Okay. So we have 2 VC minus 2 VS. So what I should do here is move everything this side. So I have a S squared plus 2S. Here I have plus 2S plus 2 plus 4. And here I have plus 2 VC. Okay.
Why didn't the 2VS at the end get a S plus 2 multiplied into it?
Oh, yes, you are right. We need S plus 2.
Oh, okay.
Thank you. Yes, for sure. Yeah, good job. So in the end, we have S squared plus 4S plus 6, the VC. Then I have 2S plus 2 VS. So this is on the S domain. So if we write everything in the time domain, we are going to have VC double dot T plus 4 VC dot plus 6 VC is minus V2 VS dot minus 4 VS dot. No dot. So this is what we have. Okay, what do we have? What do we have for this simultaneous equation? I eliminate my IL. I end up with a second order ODE in scalar form. Okay, scalar form. So I change mine in the middle using using a Laplace method. Okay, Laplace transformation method. Then we transform it back to a differential equation. So if you do a directly on this one, it may be tedious. But if you carefully do it, it should be still fine. Okay. But as you can see, this still very complicated. Okay. So that's why it is always easy to use state space. Why? You will never have a high order ODE to deal with. You always have a first order ODE. You always got a first order ODE. Okay. First order, you only have one dot. Okay. You don't have a double dot like here. Yeah, double dot. So it's messy. So so that's why state space is more welcome and especially nice in the Simulink. Okay. So that's for state equation. Then we already decided what is my state variable. For the A cross variable of A type element, C is A type. IL is through variable of a T type component, storage component. So this is called state equation, how the state evolves over time. But we haven't defined, so we defined in this one here as in, okay? What is out? So usually here looks like, this is like you connect this one to a load. So then we decide IL is my out. I care about what's the current flowing on my resistor, this 1 ohm load IL. So if that is true, so it's the voltage along there. So I check, I may have two things I care, okay? Instead of just the voltage across the capacitor, I care about it. So I care this. But also I care about this load, 1 ohm, okay? 1 ohm. So the 1 ohm is the current times 1. So the current times 1 is IL. IL is my state variable. So, so here, luckily, these two will be just, so this is my C matrix. And in here, my input signal will not directly contribute to my output. So this is 0, D is 0. And C happens to be an identity matrix. It's fine, okay? So the output equation is not necessarily 1, you can have 2. Okay, so this is 2 variables you care. But if you say, oh, I have 3 things I want to care, it's fine. It's also, you can do it. So then the system will become a multi-output, okay, multi-output, multiple output. But for input, only have 1. SIMO, single input, multiple output. So this is, you have only single input. So you can see that. So then, so no matter how complicated the system, the circuit is, it's always possible in a neat, unified form of this A, B, C, D. So that's why it is beautiful. It is beautiful, unified. So that's, I hope everybody get used to this modeling principle. And again, we use this, the similar step we reviewed in here, okay? City space model, okay? We talk about it. But at that time, last week, when I say this, you may feel, this is so abstracted. So now you see a real example. So I hope you feel now much more comfortable with all the steps. So again, step 1 is important. You need to identify which one is used for state variables, okay? Questions at this point? It's just one method for taking 2 separate equations vector into a single. Yeah, this is just, some students may say, oh, this looks scary. I'm getting used to this one. I don't like this one. So that's why you are in higher education. So you need to generalize your space of living, not only in just 1, 2, 3D dimension. You actually can live in n dimension. You learn linear algebra. Okay, so you can have n vectors in here, right? This A could be n by n square matrix. Okay, the vector x can be n. So just be careful when you stack this together and start to follow these equations and put in the numbers. You need some, in the homework, you have some practice on that, okay? Again, probably in this example session, I do it, is using the RC network. They looks very simple, but the message is you can do any complex networks. So you can draw the linear graph. This is already like a linear graph, right? Now we have KVL, KCL. We know this one very well. Okay. What I'm trying to say is, in the example we have shown in here, to me, there's no difference for mechanical system versus the electrical system. Okay. You just get used to the way of thinking here. Follow these steps. Okay. You need to practice in homework. And this part of the modeling will definitely in your final exam. This is your foundational technique. You should know it, okay? You should know it. Because these are just our starting point. I know some people may feel better to live without state space using a high order and ODE, but it's hard to analyze, okay? It's hard to analyze. So I suggest you get used to this first order differential equation first order differential equation of vector form, okay, of vector form. All right, this is our first example. I feel like it's a warm-up of your ENGR 065, okay? Our next example is non-trivial, okay? Please pay attention and wake up. Try to stay awake. So this example is a little bit different, okay? Although it looks simple. So you can see that I have a circuit like this. So this is another example, okay? So your storage element, of course, it's very strange. I have to do this so I can do it. All right, can you see this one now? You have a storage element in here. You have also storage element in here. According to our rule, you have A type element. You have T type element. So what is A type? It's A cross. What is T type? This is through variables. So this is my L, okay? And then what is the R? R actually called D type, right? The dissipate, okay, dissipate. So according to, so for a system, in front of us, we have a system. We don't call it circuit anymore. Why? Okay. Resistor, yeah. So this R1, R2 resistors, okay, they dissipate energy for D type. So you have source, it's no longer a DC, it is any signal, okay, any signal. So we treat this as not as a circuit, but as a system. Why? System is I can define what is input to the system. So this is the in, okay, the input system. And also define out, okay, in and out. So if I change my UT in, then the Y of T will also be different, right? So these are called a system with one input with one output. So it's also called SISO system, single input, single output SISO system, okay? So we want to understand how this system, it is dynamic for sure, how they evolve according to a governing relationship is a governing ordinary differential equation. So to find out that equation, process is called modeling. You want to do the modeling, you need to follow again the modeling steps, okay? Steps. And usually we prefer state space modeling. This is systematic, okay? And you end up with the first order differential equation of vector type, always first order. So we are going to do that. So, okay. All right, so we're going to move on. So this is IRC driven by a voltage source. So the question is, what is the order of the system and why? So actually we are talking about dynamic system. Dynamic system. So this is a dynamic system. Then what is the order? So this is the first question. You think about it. I'll give you an answer in a minute. The second question is, can we try to find out the high order dynamics between U is input, Y is output? And what are the A02, A1, A0, B1, B0? What are those? Okay, how to derive that? Then another one is, we assume that this is the same thing. We introduce an X, and suppose this is equals U. And then we can use XX dot as a state vector and derive ABCD. What is my ABCD? Again, ABCD is a state space model. It's a state space description. So that description is never unique. Do you understand? So that's why they ask you to do an auxiliary differential equation like that. So you may ask, what's the physical meaning of X? I would like to say no, don't ask. We'll find out later, but there is no clear physical meaning here, okay? So people also ask why you cannot use y and y dot as a state vector, okay? So that's a very good question, okay? We'll come back to that one later, okay? So now we are talking about why for the system in here, we cannot use current IC through the capacitor, nor the derivative of the output y dot as a state variable. Why we cannot use this as a, so like I said, can we use y dot as a state variable? Okay. Why we cannot do that? Okay. So this is a very serious question. Okay. So remember that when we talked about A-type or T-type, we talked about this V, okay? So in the capacitor, we know that it's IC here is C dV C dt, okay? C dV C dt, okay? But so just imagine that for any system, IC no matter what cannot be what? Cannot be this infinite, right? Cannot. In physics, you cannot make your current infinite. Okay. So in that sense, that means the VC, if you have VC has a step like this. So you have time axis. So this is your VC. Suddenly jump from here. It's called step sudden jump. Sudden jump. Then tell me what is the derivative at this point. dVc dt will be infinity. So IC will be infinity. So because IC cannot be infinite, that means VC cannot jump. Okay, cannot jump. But we already said in here that we should choose a cross variable as a state variable. The VC should be state variable. Okay, so in other words, a state variable chosen, okay, cannot jump, cannot have a sudden change. So if you have a sudden change, you lose the legal position to serve as state variable. Make sense? So if we find out a variable can jump, that means you cannot serve as a state variable. Because you state variable, you have a ddt, then that will cause infinity, you have jump. Make sense? So this question is a typical question from our homework, but I pull out to clarify a few things in the state space. So also because of usually you don't have derivative term in this side. What's the consequence of this one? So we are going to do this one in a week number maybe 4, 5, 6, 7, number 7. Oh no. 2 weeks later, okay? 2 weeks later, I'm going to talk about this one in a more general sense, okay? So how to deal with this one in the state space A, B, C, D, how you can do it. So let's move on and try to solve this. The first question, the answer is, So the answer is, I hope you'll pay attention to this term here. Because you have an independent energy storage, L and C. They are not the same, okay? Okay. So output may be expressed as an algebraic equation of the two states and the input, okay? So they are not independent. So in other words, so if you have a system, you have a capacitor, you cascade another capacitor, or you do another capacitor, and then you put out in the loop here. So you have three capacitors, so they are not independent anymore. Only this equivalent capacitor is independent. Okay, okay, be careful. Okay. So in general, if you don't have such kind of scenario, then you just count how many such energy storage element in your circuit. Then you call, so then you have 1 and 2, then you know the system is second order. Okay, second order. So it's a second order. It's a second order, okay, second order. Because you have two, the most important term here is independent, okay? Energy storage elements, okay? So how to do this differential equation? This is not very hard, okay? So the main loop equation, we can do this main loop equation. Let's do this. So this is the main loop equation, and this is inner loop equation. This is saying that. So the voltage here will be the voltage on here and the voltage on here, okay? So this is already VC, this is Y. Y plus this one. This one is IL and IC, okay, add together. So the IL, IC add together times the resistance plus the Y equals U. So this is a this is the simple loop, okay? So for the smaller loop inside, so you have a voltage, okay, VC. This is a Y is my VC, okay? So basically it's something like this. You have a source, you have something here. So then you have something here, so you have this one here. This is the topology. So this is my U in here, is from here to here, my U, and this is my Y, okay? The voltage, okay? So U equals Y plus this R1 times this the current in here. Current in here, so this is IC, this is IL, okay? That's it. For the smaller loop, then you have a voltage here, Y equals the IL, this is IL times the R2, this R2. And di dt times L is my VL, okay? Okay, so then I have these two together by constitutive equation for C is a dy dt is IC. So IC here, you put this IC here to inside here. So then you end up with U divided by R1 is RL. You have this one is dy dt times C. So it's a dy dt times C is IC. And Y divided by R1. So you have this. So divided by R1 both sides, okay? Maybe do this. So divided by R1 both sides. So you have Y divided by R1, U divided by R1. You have RL left, IC is C dy dt. Okay, because of this constitutive relationship. Then after that, you can put this into IL. So you have IL here, okay? IL here. You replace RL into here. So you can solve the, sorry. You can solve the RL, then you put this RL inside here and here. So you can get the Y relationship versus U. So you end up with Y equals this type of thing. So you have second order derivative from here. So you end up with the Y double dot, Y dot and Y, and U dot and U. All these are coefficients. So therefore you compare, you get all these coefficients. So that's ENGR 065. Okay. So you get a higher order derivative, a high order ODE. Okay. So this is a higher order ODE. Okay. So you have higher order ODE, and this is your high order ODE. Yes, I can do this, which is good. But the question is, how can I write A, B, C, D? We probably will argue why I just use Y dot. Life is easier, okay? But how you can do the du dt then? Okay, we never use that. So here's the way we handle it. Okay. So what we try to do is, this is just assuming that this is, remember, this is a copy of the left-hand side. So this is, Eris is A2, A1. So let me repeat. We are facing a equation is A2, Y double dot plus A1, Y1 dot A0 plus B1 U dot plus B0 U, right? So this is something we have, okay? This is something we have. So now, from here to ABCD is not straightforward. Therefore, we need to find a way out, okay? How we do that. So because what? Because we simply borrow this side and put an X. X you don't know yet. So let's don't ask what is X. We assume we put something X, then we have, okay? Then we have Y, okay? Then we have Y. So what is this one? So we assume, this is assume, okay? We assume this is okay. Because you can choose X to represent the U. And it happened to be the same format like this, but not Y, it's X. Don't ask me X yet, I'll tell you later, okay? Because U is like this, so the whole system is like, you're gonna give me U, I give you Y, right? So this is my system. So now we are doing something different. So we are doing something like this. I'll get a U, you do something, you get me X, then you do something, you get me Y, okay? Get me Y, right? So the X is like intermediate. So actually, so something in between, okay? So I hope this is an interesting understanding. So we can say that this together is that box, okay? Okay. So what is inside this box? We know it, but what is inside here? We don't, okay? So let's do what we have here. So what we are trying to do here is we write down, okay? We write down, this is, XX dot is my state vector. I'm going to write state vector in terms of a state equation. So I can clearly write in terms of x1 is x2, Okay, so this is basically saying that x dot is x dot. Okay. Okay. X1 is x. Okay. X2 is x dot. So this is trivial. But what is x double dot? This is like x double dot. Okay. While x double dot is here, you move everything on this side. So it's u divided by a2. Okay, u divided by a2. And here move the other sides in here. So you have a, so then again, this is x dot, okay? X dot. So then we can write AB. So this is like x dot equals, so this is d dt, okay? So you have also x dot. So this is x, this is a capital X dot. This is a capital X. So the capital X is my x dot, right? So it's a vector. Oh yeah, it's here. Okay. So what we put it here. So clearly, so what is here is a minus a0 divided by a2 times x, and here is minus a1 divided by a2 times x dot. Okay, x dot. Then oh no. So this should be this should be on downwards. Sorry. So this should be x dot should be just x dot. So this is 1, this is 0, okay? X dot is x dot. This one is minus a0 divided by a2. This is minus a1 divided by a2. Then plus this one, you have a 0 times u. You have 1 over a2 you see here. So this is exactly the a, this is exactly the b. So I just write the second order system like this, okay? But this is not what we want. You give me an x, you give me u, you can check your x. What I want is my output, okay? So this is my output equation. Output equation actually is bx0 bx dot, okay? Okay, so by doing that, okay, so it becomes a state equation versus an output equation. So my C becomes a B0 and B1, okay? So then in the end, you have X dot is AX plus BU and Y is CX. So this is our state space relationship, okay? So you may still wonder how this is possible, why we don't use capital X here, why the capital X here is not Y and Y dot. Okay, so remember, Y is the voltage, Y is the voltage across the capacitor. This is the Y, okay? But what is Y dot? Y dot is IC, okay? IC, okay? Y dot is IC. So you are asking that your IC cannot be jumping, which is not true. IC could jump, okay? IC could jump. So we are going to come back to this example probably again, okay? Why we do this, assuming this way, then we do a state space for this, then we do Y becomes the output equation. I think if you are really curious, I should tell you right now, okay? I should tell you right now. So in fact, if you know the transfer function, okay? So you know that this is input and output. What is Laplace for this? It will be a2s squared plus a1s plus a0. Then capital Y of s is b1s plus b0 the U of S. So Y of S, U of S is what? Y of S, U of S is B1S plus B0, A2S squared plus A1S plus A0. So this is called a transfer function here. So output divided by input, okay? But this one actually can be written as ys equals b1s plus b0 times x of s, okay? While x of s is what? X of s is times us. So if you insert x to here, you still get the same, right? Okay, do you? Okay, all right. So that explains what is real, why we need to introduce x. It's because we split the numerator and the denominator, okay? So basically y of s is b1s plus b0 divided by a2s squared plus as plus a0, a1s plus 0 times us, okay? So we treat everything inside here as x, right? So that's why we multiply this term in here. That's why we have x, a0 x double dot and a1 x dot, a0 x equals u. And y output is b1, b0x and b1x dot. So now you completely understand why we have these two, okay? So basically we are splitting this one. So this is like a of s divided by b of s, a polynomial. In here, a of s is b1 s b0. So it's the same. So basically what we are doing here, this is u times 1 over bs. Then we put as in here. And in the middle, this is x. But it's the same, right? It's the same. So by doing this way, we eliminate the u dot. Do you see that? We don't have the u dot. We don't have u dot. Okay. I know this is a little bit off the way, but indeed, this is the right way to go. We haven't still answered the question why we cannot here. Why we cannot use y and y dot as a state vector? We need to answer this question. Again, as I said here, state variable cannot suddenly change. Because if you suddenly change, your ddt will be infinite. Okay, it's illegal, anti-physics. All right, so now we are going to go to the next interesting point. So no matter what, you have in and out. So you can write your state model like this. Okay, so this is called state model. So if x can change instantaneously, I mean jump. Okay, then x dot will be infinite. Okay, so the right hand side of the equation would be infinite. So this should be infinite. So this is not physically realizable. Okay, we call it not physically realizable, meaning anti-physics. So it should not be. So we can say that, we can conclude that a state variable cannot allow it to change instantaneously from, if you have a finite change in the input. So I can give you an input, but inside of this is u, and you have y, and the state variable somehow in between cannot suddenly go because the x dot the u dot will go to infinity. Okay, so you cannot have a u dot at all. Okay, so you need to find a way to avoid this. Okay, to avoid this. But input is okay. Input is okay. You can change. So from that perspective, let's study from 0 minus to 0 plus. Okay, so you have there's a left hand side and right hand side. So we do this integration. So this is always finite because your input cannot go to infinity. Okay, and also the y cannot go to infinity. Okay, even at all times. Otherwise, it will be anti-physics. So the last term on the this is LHS means left-hand side. This is left-hand side. This is the last term on the left-hand side, okay? And the last term on the right-hand side here. Because this guy's y and u are finite, okay? So therefore, that integration should be 0, okay? So this should be 0. The reason this should be 0 is because y and u will not go to infinity. You don't have infinite jump, okay? You don't have an infinite value, okay? They are finite. So otherwise you have system, you have an infinite stimulation, or you have infinite output. That's already anti-physics. So these are y less than infinity, u less than infinity is a physical requirement for a system. So I didn't say it's changing. I said it's its own value. Okay. So therefore they should be 0. So this should be 0 because they don't have an infinite point. Okay, that's true. So by double integrating the input output relation from this one, you integrate multiple times. Okay. We can argue that y cannot change instantaneously. Okay, so the y will be a valid state. So y is not changed from immediately. Okay, so therefore it's okay. So because y is not changing instantaneously. Okay, so therefore y is qualified to be a state variable. Y is a valid state variable. The second term on this is the second term here should also vanish. So which is true, okay? Because you have y dot integration, okay? The second term is because on the other hand, so because you have a u dot, okay? If you change instantaneously, okay, then y dot will also change instantaneously, okay? So because u could change, because like a step, okay? But this step will result in my y dot also instantaneously change. Then that means your y double dot will blow up to infinity, okay? So y dot will change instantaneously. Therefore, y dot cannot be a state variable. Do you see that? Because u can be changed instantaneously. You have input signal can have a step change, sudden change, which is fine. Like you turn on and off your switch, which is fine. But in this case, this current IC cannot be used as a state variable. Cannot be a state variable. However, RL could be a state variable. Okay. So that answers the question, like why we cannot use my state vector is y dot y. So this is not going to work, no. So that answers about this argument. So I think we spent quite good time going through the simplest state variable in here and using a state space framework. Or you can see this is a linear graph theory, okay? Then we went through a little bit harder problem. Why this is harder? Because if you're starting from the differential equation like this one, it's not straightforward to have a state space realization, because you got this one dut dt in here. Because of this term, your y dot cannot serve as state variable. So one of the interesting idea is to assume u equals this one. And the solution didn't explain. I inserted the explanation to you that why they choose that way is because of the transfer function. Because this transfer function like this, you can equivalently write two parts, the numerator part and the denominator part. Denominator part times u is my x. Then the rest is y equals this one times x. So this becomes my state equation without u dot, okay, without u dot. So x dot, we can do a legal state space variable because we don't have a u dot, okay? So we further justify why y dot is going to change instantaneously, okay? And also I go through this figure to show you this is possible. Well, so I hope the two examples thoroughly will set the foundation for you, at least to do the state space modeling, writing, establishment using standard procedures we have seen here for circuits. For mechanics systems, you should be able to do the same. Please read some of the linear graphs examples for mechanics system in the textbook and do the homework accordingly. So you should be equally fluent regarding mechanics system modeling versus electrical circuit system modeling. So again, you need to identify in and out, what is the storage element, energy storage element, and they are independent variables. With that, I'm going to go to this part about our quiz. So in this quiz, actually it's simple. So basically you have two, if you have voltage divider, so then the ratio is the same. So you have 0.5, right? So this is a stage 1, this is stage 2. You use the red line, two red wire to connect them. So then you have I treat everything as a whole. Then from V4 to V1 is 0.5 times 25 or not, okay? So the question is basically to check your question is better. Oh yeah, V4 divided by V1 is what? Okay, so enjoy and don't refer anything else. Just use your what you have learned. Okay. This question will motivate our study of op-amp. Okay. So op-amp stands for what? Operational amplifiers. So in other words, we're going to learn amplifiers that can perform operations. What are the operations that we're talking about? What are the 4 basic operations? Okay, multiplication, division, summation, and subtraction, right? So these are 4 operations. But what about integration and differentiation? It's also a kind of operation, okay? So my answer is all this can be done by op-amp. So in other words, you just put op-amps and link it wisely, and a lot of op-amps, and you can do a lot of operations. You will be able to do computer, because computers used for operations like summation, multiplication, and so on and so forth, right? So you are right. The initial computer is not digital, it's analog. So they are actually used lots of amplifier or op amps to construct analog computers to solve the ballistic trajectory of a cannon or shooting a bullet, how they should move, or shooting a ballistic missile, okay? Trajectory, ballistic trajectory computation and prediction. So the first computer, ENIAC, is exactly a bunch of op amps, okay? So we should start to learn the op amps, okay, as our very important component in mechatronics. And I plan to use op amps to bring you up on signals and systems and signal processing. Okay, that's our main task in the next 2.5 weeks. Okay, yeah, or 1.5. Okay, 1.5 weeks. Anyway, so I'm going to stop here. If you don't have anything you want to talk, ask. Let me see. There's a chat box message. Do we then solve for those roots? What roots?
Oh, when you were doing the transfer function.
Oh, we're not there yet. You are way advanced. Those roots are called poles. We'll be there in about 3 weeks' time. Okay.
Oh, okay, sounds good.
You
Thank
will
you.
play with those roots. Okay, I'll teach you on that. All right. Okay. So too much time, over 2 minutes. Would you be in today's lab? I'll try in the evening. Yes. Usually, if I'm not occupied, I'll be there and listening. I'll keep quiet. Okay. See you maybe tonight, or otherwise, see you Friday. Bye-bye.